Hi, everybody. This is the video for week one for Math 4400. So just as, excuse me, just some reminders. Your first homework is due Monday, January 16th at 11:59 p.m. Just as I mentioned at the end of class, I put a couple of hints on the assignment page on Canvas for a couple of exercises that we didn't talk about as much in class. And also there will be a quiz on this video due Tuesday at 8:30 a.m. You do it online and the link will be active pretty soon after this video is posted. Before getting into anything new, I just want to highlight the key takeaways from this first week. So one, of course, you should understand how the class is set up and what's in the syllabus. If you haven't reviewed the syllabus already, please go back and do so. And then mathematically, well, we started talking about some basic counting. We introduced n factorial and talked about how that's the number of ways to order n things. We talked about the binomial coefficient n choose k. We gave sort of a formula for it in terms of factorials, and then also talked about how we can interpret that as a number of ways to choose k things from n things. We talked about proof by induction. So we gave some examples from that, and you have some more exercises on your homework. That's an important technique that we'll use again later in the class. And we talked a little bit about the importance of making computations to find a pattern and guess an answer when you start working on a problem. So in this class, we're going to have sort of lots of these open-ended problems. We're asking you to just start exploring something. You saw that already this week. And a lot of times, like the right way to start exploring it is just sort of work out some examples for some like small values and see what you get. And then if you notice a pattern, then you can start looking for other tools to help prove your answer is right. So like one tool we'll have at our disposal now is sort of induction. You can sort of often use that to prove some guess for like some formula for something is right. We also talked about like these kinds of like geometric arguments you can do, and we'll sort of discover different ways of justifying ideas as the course progresses. Okay, so those are sort of the highlights from this first week. What I want to talk about now is a little bit more on Clubtown. So let me recall from class on Thursday. So this was what we were working on towards the end. It was exercise 3.3a on the week one worksheet. And so here we're talking about Clubtown with the following rules. So, well, the first rule is just the standard one that two clubs are the same if they have the same members. So a club is determined by just who's in it. And then the second rule is any club must have at least two members. And then the third rule is that any two clubs can share at most one member. And when we talked about this, you guys sort of split up into groups and you spent some time looking for maximal systems of clubs. So what do I mean by that? Well, a system of clubs, I just mean you form some clubs with the people in the town that obey the sets of rules, and a system is maximal if there's no way to add any more clubs. So a maximal system of clubs is sort of when you form some clubs and then there's no way to add any more while still following these rules. So you guys found some interesting examples in the class. So if I call my residents of Clubtown 1 through n, then one example of a maximal system is actually one just contains a single club, and that single club has everybody in it. So that club with just everyone, the club 1 through n, so the everybody club. And if you think about that, there's no way to add another club to that system without breaking one of these rules, because if you add a club that has two members in it, well then, since those two members will also be in the everybody club, you're going to violate this third rule. Good. So that was one example of a maximal system with these rules. Another example you guys found was the set of sort of the collection of all the clubs with exactly two members. So like 1 and 2 is a club, 1 and 3 is a club, and so on. So 1's in a club with every other person, just a club of 2, and then 2 is in a club of 3, and 2 is a club of 4. So every pair of people forms a club. And if you think about that for a second, you see you get n choose 2 clubs that way. And again, we talked about this in class, and a little bit of thought will justify for you that that really is a maximal system. There's no way to add another club to that. So this is a maximal system with sort of n choose 2, so quite a few clubs. So okay, we explored that, and there's a lot more you could explore with this problem. Some natural follow-up questions are there larger maximal systems? Is this sort of pairs maximal system? Like, is that the best you can do? Is that the most clubs you can get? Or is there some clever way to get more clubs? So that's a direction you could explore this. You could also ask, can you find maximal systems of any number between 1 and n choose 2? I mean, like we have a maximal system of 1 club, we have a maximal system of n choose 2 clubs. Can we find, can we hit like any number between those? So there's lots of interesting things you can think about with this. But we're going to sort of stop exploring this set of rules here. And I want to change the rules a little bit to get to sort of something sort of an interesting and surprising connection. So I'm going to change that last rule. And so now, instead of having any 2 clubs can share at most 1 member, now I'm going to have any 2 clubs must share exactly 1 member. So this, if you look on this worksheet from week 1, this was exercise 3.3b. And so what I would recommend you do right now is stop the video for 5 to 10 minutes and try to write down some maximal systems using these rules. So you can do it, and for small values of n, for example, you might like look at when n equals 5 and sort of try and write down some maximal systems and see what you get. Okay, so I'll give you a second to stop the video if you'd like to do that before I go to the next slide. Okay, I'm going to move to the next slide now. So here I've just copied the rules up here again, and now I have some examples of maximal systems. So like this 1 club maximal system where we just have the everybody club, that still works. There's sort of this third rule doesn't really apply because there's only 1 club, so we sort of don't have 2 clubs to compare. So this still works, but the all pairs doesn't work anymore, at least when n is at least 4. So maybe I should say for n at least 4. Right, because sort of if you have all of the pairs, well, some of those pairs don't overlap at all. Like if I have 4 people, the pairs 1 and 2 and 3 and 4, those don't overlap. So they don't share exactly 1 member, so that's no longer a valid system of clubs. So that doesn't work, but if you play around, you can still sort of construct some maximal systems. So if n equals 5, I could look at the following. So I could look at the clubs where I have 1 and 2 are together, 1 and 3 are together, 1 and 4 are together, and 1 and 5 are together. And then 2, 3, 4, and 5 are all in 1 big club together too. So if I looked at this, well, each of these has at least 2 members. Check, so that rule is satisfied. And then also any 2 of the clubs share exactly 1 member. Like sort of all these clubs, when I look at them together, when I look at 2 of them together, they share the member 1. And then each of these clubs sort of shares the member, like this shares the member 2 with this club, this shares the member 3 with this club, this shares the member 4 with this club, and this shares the number 5 with this big club. So these do satisfy the rules. And I really couldn't add any more because if I add another club that has at least 2 people in it, well, either one of those people will be 1 and then sort of all overlap, I'll have one of these entire 2 clubs here. Or if 1 is not a person in it, then sort of the 2 of those people will be in 2, 3, 4, 5. And so sort of all intersect this one with more than 2 members. So this is more than 1 member. So this is really a maximal system. I can't add for example, yeah, good. Sorry. So this is a maximal system. Good. And in fact, if you played around with this and you sort of experimented, this is sort of the best you can do. You're never going to find, it turns out, more than n people, more than n clubs under these rules when you have a town with n people in it. So that's, I'll call it the club town theorem. If there are n residents in club town with these rules, then any maximal system has at most n clubs. So this example is sort of the best you can do, the most clubs you can make. There could be other ways to make n 5 clubs here, but sort of you're never going to make more than 5 clubs while satisfying these rules. So I want to tell you how to justify that theorem, because it makes a pretty cool connection between this stuff where somehow this sort of purely counting kind of thing we're doing here and linear algebra. So here's the proof idea. So the first step is sort of, I'm going to sort of take these clubs and I'm going to encode them in a different way. So I'm going to take a club, which is sort of just like a collection of people. And then I'm going to sort of encode it using a membership vector in Rn. So it's probably easiest to just sort of write down what that is in an example. So for example, when n is equal to 5, my residents, I just call them 1, 2, 3, 4, 5. Then, for example, the club that has person 1 and person 3 in it, I sort of encode that with the vector 1, 0, 1, 0, 0. And the club where that has residents 2, 3, and 5, I encode that with the vector 0, 1, 1, 0, 1. So here, like, what am I doing? I'm saying, like in the first spot, since person 1 is here, in the first spot I put a 1. And then since person 2 is not in this club, in the second spot I put a 0. In the third spot I put a 1 because person 3 is in this club. Person 4 is not in this club, so I get a 0. Person 5 is not in this club, so I get a 0. So like in the second spot, I'll put a 0 if the second person is in the club, and I'll put a 1 if the 0 if the second person is not in the club, and a 1 if they are in the club. So that's what you do sort of for each spot in this vector. Like the first spot, I look for the person 1. Second spot, I look for person 2. Third spot, I look for person 3, and so on. And so that sort of gives me a way to encode my clubs using sort of these membership vectors in Rn, which are vectors whose entries are 0s and 1s. Okay, and then I can use a powerful statement from linear algebra. So now that I have these vectors, like it would suffice. So if I want to show that I can have at most n clubs satisfying these rules, well, actually what it would suffice to do is it would suffice to show that every time I have a system of clubs satisfying the rules, if I take the membership vectors of those clubs, then those are linearly independent. And the reason is, so let me recall this basic fact from linear algebra. If I have some set of m vectors in Rn, well, if those are linearly independent, then m is less than or equal to n. So this is some basic fact, basic foundational fact from linear algebra, that you cannot have more than n linearly independent vectors in Rn. So if I could show these membership vectors were linearly independent, I would know I had at most n of them, so I would know I had at most n clubs in my system. Okay, so in order to understand that, well, I need to translate these rules into something in linear algebra. So I can do that using the dot product. So we recall just out loud, the dot product of two vectors, you just sort of add up the products of their components. For example, like this rule 2 in terms of those dot products, that any club must have at least 2 members, just becomes when I sort of dot one of these membership vectors with itself, this is greater than or equal to 2. So like, for example, I look at like this club 1, 3 from the last slide, whose vector was 1, 0, 1, 0, 0, then, so that's its membership vector. So v dotted with v is equal to 1 squared plus 0 squared plus 1 squared plus 0 squared plus 0 squared is equal to 2. So the point is, when I take this dot product, the membership vector of itself, I'm just going to get the number of members in the club. Okay, and similarly, if you sort of play around with this, what you'll find is when you take the dot product of two different clubs, the dot product of the membership vectors for two different clubs, this is just going to be the number of members in both clubs, in the overlap, or the number of members shared. I mean, somehow, like, you're going to have a product, like, when you do this, you're going to get, you do this dot product, okay, let's do an example. If I have like 1, 3, okay, I'll do an example of 1, 3, and 2, 3, 5. From before, so 1, 3, this is 1, 0, 1, 0, 0. Now if I dot that with 0, 1, 0, 0, 1, 1, 0, 1, So I take the dot product of these two membership vectors. Well, I just get 1 times 0 from the first component plus 0 times 1 from the second component plus 1 times 1 from the third component plus 0 times 0 for the fourth component, because this is 0 and 0, plus, so let me move that over, plus 0 times 1 for the last component. Well, every time I have a 0 in one of these, that term goes away, and I'm just left with sort of every time I had a 1 on both entries, I get a 1 here. So in this case, this is equal to 1. In other words, it's about like exactly I got that 1 because from the part that both these clubs had 3 in it. That's what gave me a 1 here and a 1 here, and 1 times 1 is 1. So in general, when I dot product these membership vectors, I'm exactly just going to be counting the number of members shared. So this rule that any two clubs must share exactly 1 member just becomes the rule that sort of vi dotted with vj is equal to 1 for I not equal to j. Okay, so I have these conditions on dot product, and it turns out this is actually enough to show that these are linearly independent. So sort of proving this club count theorem reduces to showing that if I have any m vectors in Rn whose dot products, so each vector has dot product of itself, at least 2, and then the dot products of sort of 2 distinct ones is 1, then they're linearly independent. So you're going to prove this on your homework assignment, and so there's a hint about how to do it here. This hint is also will also be on sort of the worksheet for week 2. So this is going to be on your second homework assignment. So you'll get to do that next week. Let me just point out, and you can sort of interpret these conditions on these vectors geometrically. So the dot product of a vector of itself is the square of its length. So this is sort of saying vi dot vi is greater than or equal to 2 is the same as saying each of these vectors has a length at least square root of 2. So length at least square root of 2. And then the second condition that sort of vi dot vj is equal to 1, well, the dot product of two vectors, I can interpret it in terms of the lengths of those two vectors and the cosine of the angle between them. And so if you sort of input these conditions on the lengths and on this dot product being 1, what you see is that the cosine of this angle is between 0 and a half. In other words, the angle sort of is sort of greater than or equal to pi over 3 and less than pi over 2. So somehow this sort of these conditions you can think of as sort of giving you some constraints on the angles between these vectors and saying sort of all of them sort of have sort of a certain length. Okay, great. So that's sort of how you can sort of think about this sort of visually. So somehow they're saying maybe they're not at right angles to each other, and they're not sort of pointing too close in the same direction. So they're somewhere sort of between that. So like here's like an example of sort of 3 vectors that would sort of fit this bill. And you can sort of see like these 3 are linearly independent. So you can't sort of bring, somehow this is sort of preventing you from bringing them too close to each other, too close to point in the same direction. Okay, but it's somehow you don't need this picture to prove it. Like there's just a simple computation in the end actually that will let you show this. Great. Okay. Yep, we're going to stop there, and we're just going to explore some related computations and some more ways we can use linear algebra to sort of approach these counting things, and see some other surprising connections next week. See you then.